In the last few videos, we talked about how to go about naming aromatic molecules. In this video, we're going to continue talking about aromatic molecules by looking at the unique stability that is conferred by aromaticity. So as we continue into this particular unit, we are going to, at the moment, focus primarily upon benzene as our model aromatic system. In the next video, we will start talking about additional extended definitions of what constitutes an aromatic molecule. But for now, for purposes of this video and evaluating the stability of aromatic systems relative to systems such as the conjugated molecule on the left that aren't aromatic, we're going to talk about what is the difference in stability between those two types of systems. When we are referring to the stability of a system, one way that we can analyze this is by thinking about how readily the molecules react. And so in thinking about the stability of an aromatic system that has that alternating pattern of single bonds and double bonds, we're going to look at the stability of aromatic versus conjugated systems, where the aromatic system is a special type of conjugated system where the atoms are in a ring with full conjugation all the way around the ring in the case of benzene. So looking at the stability of aromatic versus conjugated versus isolated alkenes. We can evaluate this by looking at, in one perspective, the reactions that are undergone by each of these types of systems, where if we have a conjugated system, such as the conjugated diene that I have shown here, we can react that readily with reagents such as HCl or HBr. We talked about that in the last video. And what happens is that the molecule undergoes an addition reaction, in this case at the allylic position. And in the case of this particular molecule, due to the symmetry that exists in this molecule, it turns out that there's only one constitutional isomer product, this product right here. So analogously, one would think that if we have an aromatic system, a benzene derivative, or benzene, such as this, that if we react with HCl, we might predict that we would similarly get an addition product where the H and Cl add across one of the carbon-carbon double bonds in that aromatic molecule. But in actuality, generally we observe no reaction, and certainly no reaction that corresponds to adding H and Cl across the carbon-carbon double bond. So in other words, we don't observe any product that corresponds to addition, so we're not going to observe a situation where we add Cl and H across the carbon-carbon double bond. That is absolutely, full stop, not going to be observed. And then a third scenario would be an isolated diene or isolated triene, whatever type of system you want to look at. If we added HCl across that, we would find that the H and Cl would add across a carbon-carbon double bond of that molecule to give a product such as this. So it appears, based on these three scenarios, that in all of these cases where we have an alkene group, be it isolated alkene groups within this diene or conjugated alkene groups within this diene, that we have addition reactions as a common reaction type that occurs. On the other hand, when we react this aromatic ring with HCl, we see no reaction. So this evidence supports that the aromatic ring confers dramatically increased stability to the system relative to any of these other scenarios where we just have conjugated systems within the molecule, but it's not this special aromatic system alternating pattern of single bond, single bond around this six-membered ring. So our conclusion here that we can make based on this pattern of reactions or lack of reactions that we could observe, we can conclude that the aromatic ring confers stability because it's the only system where we do not see the addition reaction take place. So we conclude the aromatic ring confers stability because we can't force addition reaction to take place on that ring. And so that indicates to us, that lack of reactivity indicates to us that the system that we are dealing with here is very, very stable. Another piece of evidence that we can use to support this notion that the aromatic system is very stable is we can compare the heats of hydrogenation for each of these three types of molecules. Conjugated diene, aromatic molecule, and an isolated diene. And if we look at the stability of these from the perspective of the heats of hydrogenation, what we're evaluating in these heats of hydrogenation are delta H naught values, is how exothermic is the reaction of adding H2 across the carbon-carbon double bond. So how much energy is released as heat during that reaction? And that indicates the stability, where the larger the heat of hydrogenation, the less stable the molecule. And we can normalize this heat of hydrogenation on a per mole or per bond basis to account for the fact that in the case of HCl, there are 2 double bonds. In the case of, this diene, there are 2 double bonds. In the case of the aromatic molecule example of benzene, there are 3 double bonds. And so we can normalize the delta H based on how many double bonds there are in that molecule to conceivably have hydrogen added to in this hydrogenation reaction. And if we look at those heats of hydrogenation on a per mole or per bond basis here, what we would find is that the highest heat of hydrogenation corresponds to the least stable molecule, which is the isolated diene down at the bottom of the screen here. So this would have the largest delta H value. What that indicates to us is that this is the least stable of the molecules. It is the least stable because there is no resonance in that isolated diene. Then second in the list, if we were to experimentally measure the delta H values, would be this conjugated diene up top here. It's going to be in the middle of the road for the delta H value because it does have some resonance where we can delocalize the electrons across this conjugated system. That was the key to the stability of conjugated systems in the last chapter, was that they're stabilized by resonance because we can draw multiple resonance structures indicating the delocalization of those pi electrons. And then the third ranking here, that is the lowest delta H value of all of them by far, is the aromatic molecule. And the low delta H value for this is so low, meaning the molecule is so stable, that it can't be accounted for by resonance effects alone. Because one might look at this molecule, the aromatic molecule, and they might say, well, there's additional resonance structures for this molecule since it has the 3 conjugated double bonds relative to the scenario up top here where we only have 2 conjugated double bonds. So one might be inclined to say, oh, there's more resonance structures possible here, so therefore that structure is more stable. And while it is true that there are more resonance structures possible there, that extra opportunity for resonance does not fully account for the fact of how stable this molecule is. That is an extremely unusually low delta H value. It has a very small heat of hydrogenation, indicating that it's very, very stable, more so than could possibly be accounted for by the delocalization of electrons by resonance. So there's something else going on in this aromatic system that confers that additional stability. So why is it then that benzene is so stable relative to other structures that also have alkene groups and have alkene groups conjugated? Well, when we think about the structure of benzene, we have our 6 carbon atoms in a ring here. The ring is trigonal planar at every single carbon atom, meaning that the structure of benzene is completely planar. It lays completely flat here. And when we have a continuous system of sp2 hybridized atoms, where they are laying flat, where the structure is flat or planar, what's going to happen is that there will be overlapping p orbitals from each of those individual sp2 carbon atoms that are all oriented vertically, that are all oriented in the same direction. So when it's planar, that is going to allow the alignment, that is a vertical alignment in this case, of p orbitals from the sp2 atoms. And so what happens is you end up with a continuous system around the ring of these p orbitals that are all oriented vertically, like I'm drawing here, and create a network of overlapping p orbitals, both up top here above the ring and also down below the ring as well. And this can only occur when the ring is completely planar, because if the ring were not planar, then some of these orbitals would not align perfectly vertical in orientation. Instead, they would be tilted because of the fact that the carbon atom itself was not part of this planar system. And so, by virtue of the fact that this system is planar, the vertical p orbitals along this y-axis are going to align perfectly. And those p orbitals are available due to the fact that the atoms composing the ring are sp2 atoms. So what will happen here is that the benzene fact that the system is planar and allows for the electrons within these p orbitals to be totally aligned is going to create a system where the electrons within these groups all occupy low energy bonding orbitals. There are low energy bonding orbitals available to be occupied. There are also high energy non-bonding or anti-bonding orbitals. And in the case of benzene, what happens is that due to the fact that there are 6 pi electrons, all of those 6 pi electrons are able to occupy low energy bonding orbitals. So at each of the individual carbon atoms around the ring here, we can think of 1 electron being associated with each of those, 1 pi electron that is, and all 6 of those will fit into low energy bonding orbitals that are aligned perfectly into this planar circular shape about those sp2 hybridized atoms. And so the crux of why benzene is so stable is because it fits these special criteria of having a planar structure that allows for the overlapping and interaction of these p orbitals due to the alignment of those p orbitals, since all the atoms are planar here, at these sp2 hybridized trigonal planar atoms, and due to the exact number of electrons that are found within this system, number of pi electrons being 6, that number of 6 is magic in that it allows all 6 electrons to occupy low energy bonding orbitals. What we will find as we go on to the next video and we start looking at additional details of why some other related molecules are also super stable and some others, even though having subtle structural differences, are very, very unstable, we will be able to relate the exact number of pi electrons in a ring system to whether the molecule will be extremely stable, meaning it's aromatic, or whether the molecule is rather unstable or extremely unstable, meaning that it is not an aromatic system, or in fact is what we can refer to as an anti-aromatic system, which is a system that is much less stable than one would predict based on the number of pi bonds in the molecule alone. So we are going to be looking in the next video at what are the criteria for a molecule meeting the criteria to have this exceptional stability. In other words, how can we look beyond just a 6-membered ring of carbons with alternating single and double bonds and extend this concept further to find other molecules that exhibit this rather remarkable stability. So in the next video, we're going to continue to be looking for molecules that are planar, which will allow the p orbitals to align, We are going to be looking for atoms that can be sp2 hybridized because that enables that planar structure to be present. And we're going to be looking for very specific numbers of electrons present within those pi bonds or pi systems that will allow all of the electrons to occupy the low energy bonding orbitals rather than occupying high energy bonding orbitals, because those low energy bonding orbitals being occupied, that is going to create molecules that are extremely stable. And so that is at the heart of why benzene is so stable relative to the other types of molecules we looked at so far, which were things like conjugated diene, where the conjugated diene is not a complete sp2 system. And so since there's some sp3 carbons there, it's going to be non-planar, and hence we can't have that ideal alignment of p orbitals. And the same would be true with an isolated diene, where the electrons from those p orbitals are not going to be able to line up properly either because of the non-planar nature of the structure. Likewise, if we had a molecule that was acyclic, meaning a linear system of conjugated double bonds, that too would not be able to exhibit this extreme stability or aromaticity, as we call it, because of the fact that we could not have this perfect circular alignment of all of these p orbitals into a network. So in the next video, we'll go through in detail what we refer to as Huckel's rules, which are a set of guidelines that we can use to break this down and evaluate any molecule based on a certain set of criteria to evaluate whether that molecule is aromatic or not. In other words, whether that molecule exhibits this extreme stability.